Okay, so welcome guys. So this is part of the lecture series for the general properties of radiation detectors. And this is about counting curves and energy resolution. Counting curves is important if you want to find an operating point that have the maximum stability over periods of time for radiation detection. This is important, let's say, in a GM counter. Energy resolution, on the other hand, is important in our study of radiation spectroscopy. So let's start. We will start by discussing counting curves and plateaus, followed by the discussion of energy resolution. Commonly, we define a fixed discrimination level when a counting device are detecting pulses. This is when radiation detectors are operated in pulse mode or pulse counting mode. Signal pulses must exceed a given level of HD. So this is like a limit or a threshold level, and in order to be registered by the counting circuit. The level of HD can be varied to analyze their amplitude distribution of these pulses. In instrumentation, this can be done usually by varying the voltage supplied to our detector. A series of measurements can be done in which the number of pulses n per unit time is measured as we vary HD, which is the discrimination level. In order to get counted, you should exceed this value of your threshold, your HD. This will result to the integral pulse height distribution as shown here. So this is the integral pulse height distribution. So if we try to vary your HD, let's say we will start with a certain H naught, H1, H2 up to H5, we will be able to produce this type of distribution. For this discrimination level, we usually expect variation in its value. In actual measurement practice, it may influence our measured counts. Thus, we want to find the most stable discrimination level given this pulse height spectrum. For this figure, it is located at level H3, and at point H3, we can say that this is the most stable discrimination level. The slope of the integral distribution is minimum at that point. Thus, small changes in the discrimination level will have a small impact on the summation of pulses recorded. In general, regions of minimum slope on the integral distribution are called counting plateaus. In this region, this is our counting plateau. We have here the H3 discrimination level. It is that operation point in which we achieve minimum sensitivity to the fluctuation of our discrimination level. Now, let's have another graph. It is usually possible for radiation detectors to vary its gain, shown here, or amplification for the charge produced in radiation interaction. This can be done electronically by varying the amplification factor of a linear amplifier, which is placed between your input and output, shown here, or between the detector and the counting system. A linear amplifier is just an electronic circuit whose output is proportional to the input but capable of delivering more power into a load. Shown in this figure is the differential pulse height distribution corresponding to three different values of voltage gain. So we have here gain equal to 1, 2, and 3. We vary the gain of our amplifier. This is applied to the same source of pulses. The highest voltage gain will result in the largest maximum pulse height as shown in this figure. But in all cases, the area under the curve of your differential distribution will be constant. So for G1, let's say gain is equal to 1, no counts will be recorded because under your HD, your discrimination level, all your pulses are less than this value of your HD. So thus, we will not be able to count anything. Pulses will begin to be recorded somewhere between G1 and G2, as shown here, or as shown in this graph, between G1 and G2. An experiment can be carried out in which the number of pulses recorded is measured as a function of the gain applied, as shown here. And this graph is somehow similar to our integral pulse height. This is sometimes called your counting curve. Such plot is shown, and in many ways this resembles your integral pulse height distribution. One application of our discussion is finding the operating voltage of our GM counter. Here we have the graph of the voltage applied to the GM counter versus the number of counts recorded by the system. The count rises as we apply a given amount of voltage until it reaches a Geiger threshold, shown here. From the threshold, it is the start of this plateau, as we have discussed previously. When the voltage is increased beyond this threshold, the counting remains the same for a given range of voltage values. This is the straight portion of this curve, thus this is the plateau. This plateau continues until it reaches the excess potential, which is another threshold. This is called the overvoltage. In this part, the number of counts becomes very high, and this is due to the continuous discharge of our system. In some types of radiation detectors, such as your GM counters or your scintillation, so this is a liquid scintillation machine or scintillation counter, the gain can conveniently be varied by changing the applied voltage to the detector. There are times that we are interested in measuring the energy distribution of the incident radiation. This is generally classified as radiation spectroscopy. In this section, we will introduce some concepts important in our study of radiation spectroscopy. This figure shows the response of a detector to a monoenergetic source of radiation. So we have monoenergetic source, so which means that it only releases single energy. This is the differential pulse height distribution that might be produced for a good resolution detector and for the bad resolution detector. For your good, this is this spike, and for the poor resolution, we have this one, the broad distribution or the broad pulse. Therefore, this width of your pulse reflects the fact that a large amount of fluctuation was recorded from pulse to pulse, even though the same energy was deposited in the detector for each event. So your width is essential in measuring the resolution or the energy resolution of your detector. Now let's go to the formal definition of energy resolution. Assume that only radiation for a single energy or monoenergetic is being counted. So we have still monoenergetic source. The full width at half maximum, as shown here, FWHM, is defined as the width of the distribution at the level just half of the maximum ordinate or this y coordinate value of the peak. So this is the half, and this refers to the width of your pulse. Note that we assume that the background noise or the background radiation is negligible for this case. Therefore, your resolution can be formally defined as this, as the full width half maximum over h naught, where your h naught is the peak centroid of your graph. So your resolution R is dimensionless fraction and usually expressed in percentage. The smaller the figure for the energy resolution, the better the detector will be. Will be able to distinguish two radiation with energies adjacent to each other. So we want this one, we want this one to be small to be able to resolve pulses with energy adjacent to each other. There are a lot of possible sources of fluctuation in your radiation detector, especially for radiation spectroscopy. It can be characteristic to your detector. We can have some random noise that includes due to your detector or due to the instrumentation of the system. The second source of fluctuation is your statistical noise, and this can be due to the discrete nature of the radiation emission. Given those sources of fluctuation, so one can estimate the amount of inherent fluctuation by assuming the formation of charge carriers is governed by your Poisson statistics or Poisson process. Under this assumption, if a total number of charge carriers n is generated on average, let's say, one would expect a standard deviation of square root of n to characterize the inherent statistical fluctuation in that specific number. If this were the only source of fluctuation in the signal, the response function can be shown as a Gaussian shape, as shown in this figure, because n is typically a large number. So in this case, the Gaussian function can be conveniently written as shown in this expression. So the width parameter is given by your sigma here. That determines the full width half maximum of the Gaussian uh, with a certain relationship with your FWHM. The response of many detectors is approximately linear. So I'll just prepare my pen here. So approximately linear. So that the average pulse amplitude, so for this case we have H naught, the centroid, can be approximated by K times N, wherein your K is your proportionality constant and your N is the average number of charge carriers. So the standard deviation sigma of the peak in the pulse height spectrum can be written as K square root of N. We'll study later the popularity of semiconductor detectors, and this is due to the fact that a very large number of charge carriers are generated in these devices per unit of energy loss of your incident radiation. Hi, if you have learned something in this video and you like my content, please consider subscribing my YouTube channel, JP Academia. See you in the next video.